optimizing safety inventory, choosing the reorder point. We consider the cycle inventory, and now we will move to the management of safety inventory. Now, the management of safety inventory basically answers the question, when should we order the additional quantity? So we're going to consider this in the context of the delivered quantity, where we have replenishment that is instantaneous. Now, this model, we're going to assume that inventory is monitored continuously. In literature, this is often called a continuous review system. So what that means is that if at any point in time we know the inventory, and so you might have it monitored, for example, in the information system, and we can say at the moment it drops to or below a value called reorder point, we can order another quantity, for example, the Q that we determined in the other model, in the EOQ model. Right? So the question is, what should this reorder point be? And the answer to this is related to another term, lead time. A lead time is the time from the moment we order to the moment we receive the quantity. Right? So on this graph, it is shown as this L. It's a time from the moment we request the order to the moment we receive the ordered quantity. And of course, now the simple answer for reorder point, or ROP, is that it should be large enough to satisfy demand during lead time. And in this case, while before in the management of the cycle inventory, we were satisfied with considering that the demand rate, the average demand rate is R, now we will have to consider some uncertainty. The problem here is that if we just assume that during lead time the demand will be average, if the demand is lower, it's fine. If the demand is average, it is fine, right? This is where in the graph it shows demand is lower than average. Demand is average, it is fine. We reach zero in the cycle inventory. But if the demand during lead time is higher than average, right, then we are at the risk of having a stock out, which means basically that we sell or we use all the inventory, and at some point we run out and we still have demand, but no units of inventory are available. So we will need to consider some kind of distribution of demand during lead time, with the average being R, right? And then there's some kind of variability here. So we're going to consider a demand distribution, normal demand distribution, and we're going to assume the average of this distribution is mu L, and the standard deviation is sigma L. Of course, mu L will be related to R, but it will be it will be expressed in terms of the demand during lead time, not per week or per year, but per lead time, whatever that lead time is. So if we're given this, we can calculate the reorder point based, for example, on the in-stock probability that we desire. So the idea is the following, that I think this is our normal distribution we're considering. Now remember, normal distribution, right? It goes from minus infinity to plus infinity. So it's actually impossible to satisfy, to have a quantity that is large enough to guarantee 100% chance of not having a stock out, of being in stock. So we always have to assume some kind of large, a value that is close to 100%, but less than 100% as desired in stock probability. And if we do, we can calculate reorder point using the inverse of the normal cumulative distribution function, or the right? You can calculate this as an Excel formula where you plug in cycle service level. Cycle service level will be this probability of being in stock, and you plug in the mean and standard deviation, and you're going to obtain the reorder point, which is the value, right, the level of inventory that should be sufficient for the demand during lead time with probability CSL. If you do set it, then we can actually calculate how much safety stock that actually implies. And what I want you to see is that that reorder point, it will include this average demand during lead time and an additional premium or an extra inventory, which we'll call SS, or safety stock, right? So SS or safety stock is actually the extra amount that we're introducing here in addition to cycle inventory. And this is actually what we call the safety inventory or safety stock, right? And because we have this additional safety inventory, we will have additional cost of holding because this inventory, in an average case, it is an inventory that we will keep forever, right? Throughout the time horizon, whatever it is. So we should account for its holding costs. So if you like, to the previous costs that we have considered, which were the ordering cost, the holding cost related to cycle inventory, and we also considered purchasing cost in the case of discounts. We still have one more cost, the fourth type of cost, which is holding related to the safety inventory. So what I also want you to realize is that once we have the decision on the quantity by the EOQ model, and once we decide a reorder point by this model, we in fact have an inventory policy that says when inventory, inventory position is ROP or less, then order the quantity Q that we obtained using the EOQ model, right? So this is ROP from the reorder point setting, and this is Q from the EOQ model. That's a policy, and of course it works only if you have a continuous review system, so some kind of information system that can observe inventory continuously and react the moment inventory drops to ROP or less. Let's consider an example. Suppose weekly demand is normally distributed with R equals 700 units per week. And now we also need a standard deviation of this demand, right? So this is just an average demand per week with standard deviation 150 units per week. Suppose also that holding cost is as before and that the lead time is 4 weeks. Recall that lead time means the time from the moment we order to the moment we receive the ordered quantity. When should we order to have in-stock probability CSL 97%? Of course, the question when has to be answered by the reorder point, right? So we should say when inventory position is, and we provide a value or less than order, right? So first thing to realize is what is the distribution of the demand during lead time? So demand or mean demand during lead time is mu L equal L, right? How many weeks times R, right? So lead time is 4 weeks and demand per week is 700. So it will be 4 times 700 equals that's 2,800, right? So that is the number of units. We could say per 4 weeks, we're just going to keep it as a value without unit, but remember this is number of units per the duration of lead time. Now standard deviation of demand during lead time, which is the other value that we need, is sigma L, right? Now this is also related to the sigma per week. However, we have to somehow aggregate 4 weeks of random demand, and if we assume the demand in each week is independent from any other week, then the formula to be used here is square root of lead time times sigma. Right? So basically, if they are independent, the sigma in 4 weeks is not 4 times the sigma of 1 week. It is actually square root of 4, which will just double it. So right, so it will be 2 times 150 equals 300. Right, so we have the demand distribution. We are assuming it is normal, and right, and so for 4 weeks it is also going to be normal with this mean and with this standard deviation. So now we are ready to calculate the reorder point. As we said, is the inverse value from the normal distribution with cycle service level, which we assumed to be 97% with the mean mu L and the standard deviation sigma L, standard deviation of demand during lead time, and that is going to be norm inv, plugging in the number 0.97, right? This is the 97%, 2,800 and 300. We're going to get a value 3365, which is actually, I always remember to round up this value. Why? Because if you round it down, you're actually going to obtain probability that it's slightly lower than 97%. If you round it up, you're going to exceed this probability, 97%. So if you really want 97%, you're probably going to be more satisfied with overachieving than not delivering exactly 97%. So if this is the reorder point, so what does it mean, right? I mean, if you consider that this is the same example as we had before, and let's say we were ordering 8,015 units, this tells us when we should order these 8,015 units, the optimal quantity Q, when inventory drops to or below 3,365 units, right? So that would be the inventory policy. Order Q, let's say Q 8,015 that we determined before, when inventory is less than or equal 3,365, which is the ROP, right? We also can think or ask ourselves a question about safety inventory or stock. Safety stock SS is what? ROP minus the mean demand during lead time, right? Remember, ROP is trying to satisfy the demand during lead time, which on average will be sigma L, but if it is higher, then, right, we have the safety stock to cover, in this case, the excess. So it's 3,365 minus the demand during lead time is given here. So that's minus 2,800, and that's going to be 565 units, right? So our safety inventory is 565. It's a constant, and it's also an average inventory. So additional holding cost for this safety inventory is SS, right? SS times H, and that's 565 times 0.006538, right? This is the holding cost that I'm taking, right? So this is going to be an additional $3.69 per week, right? So this completes the analysis of the reorder point and the valuation of the safety stock and its additional cost. So if you recall, before we had an ordering and holding cost of $52.40. Now we have to add additional $3.69 per week due to the safety stock, which will allow us to be in stock, to not have stock out in 97% of all the cycles.